Hi. So last thing about Taylor series that we haven't discussed yet is the reminder. And look, of course, this reminder, if we use linear approximation, quadratic or cubic approximation, can be, of course, we know it's going to be bigger the further we go from the point of approximation, on one hand. Well, and we know that except for the fact that this is our error, it doesn't bring much useful information. However, there is an exception for this one. And it turns, and it happens when we deal with Lagrange form of the reminder. Okay, look, imagine that we've got a Taylor series, right? So we are expanding the function at some point x0, and we will get that this is f of x0 over 0. Factorial plus f prime of x0 over 1 factorial x minus x0. And we go on like this until we would go end up at nth derivative evaluated at x0 over n factorial and x minus x0 n. Right. In this case, we could say that there is one element missing, right? The reminder. Now, how many elements do we have? N, right? Now let's just say this n is a very, very big number, right? Now, what Lagrange proposed is to express this reminder in the following terms. Look, what do we see over here? This is the Lagrange form of the reminder. And it actually very closely resembles elements from the Taylor series, right? Here we've got n derivative. Here we've got n plus 1 derivative of phi. Here we divide by n factorial. Here we divide n by n plus 1. Here we are taking to the power of n plus 1. Look, it all makes sense. Like, what we are actually adding up is the next element that would totally fit in here, right? With one exception. P. What is P? P is generally some number between x and x0. So at the point of expansion, x0, and point of evaluation at x. Look, we usually do not calculate it per se. What we want to do is to assess some properties of this reminder. And look, let's assume a case like this. N is approaching infinity. How many components will we have here? Well, infinity, right? So if we are trying to approximate some function, doesn't matter what, using Taylor expansion, right, with n elements, we have n different expressions. Now, look, if we've got n and n is going for infinity, it means that we are allowing each next consecutive component to give us better and better and better and better approximation of an original function. However, infinity is a very big number, and we don't even actually understand it in its entirety properly. However, we can figure something out. Because look, we would like to have as good approximation of a given function as possible. approximation would be perfect, remainder would be 0, right? So let's consider the case that we've got over here. Look, if it happens to be that we are trying to approximate one function using a second function, right? Using our Taylor series. However, we've got we are allowing ourselves to have n plus 1 different expressions, right? So we will have plenty of expressions. We would assume that we will be getting better and better and better approximation. However, the question is when this approximation can be perfect. And the answer to this question is very simple. When there is no remainder. However, how can we check? Well, this is where Lagrange form of the remainder is useful. Because look, if I'm going to calculate the limit with n approaching infinity out of Rn, and it happens to that this limit is exactly 0, then what does this imply for our function? It implies that Pn, so polynomial of the degree n, is equal to v of x. So look, what we learned just above now is that if we are taking some arbitrary function and we are using Taylor expansion with infinite amount of elements, then if with increasing number of elements a value of the remainder goes to 0, we know that the polynomial we are using is a perfect representation of that initial function. And look, the thing here is that the thing that we've got over here is that actually this we don't need to calculate the series. All we need to do is to find the expression for the remainder, calculate its limit, and this is it. Actually, we're going to be using what I've just said quite a lot in different classes. But let's summarize everything we said, and we get our final theorem associated with Taylor series. So, if limit with n approaching infinity out of the Lagrange form of the remainder is equal to 0, the Taylor series can be written as convergent infinite series in the following form. Right? Of course, here we will have more and more and more components, right? And we will have third derivative, and so forth. So this is an infinite series. So, but this infinite series is called convergent. What does it mean, convergent? In this case, I will explain later. For what you need to remember about it is only that convergent means that if we have big enough number of elements in the series, it gives us a perfect approximation of this. How many elements? Well, a lot. Infinite. However, those elements, assuming that the limit of the remainder is 0, will be getting smaller and smaller and smaller and smaller and smaller. So, if we have enough elements, they go to 0. Okay, thank you very much. This is it about the Taylor and Lagrange series. Now, the next subject we're going to be talking about is customer choice theory. However, in order to operate within this area, we need to use again Lagrange, but this time Lagrange multiplier and the technique of constraint optimization we discussed in mathematics. So, what you're going to see next is a review of what we said about the optimization under constraint, and since the next week we're going to start customer choice theory. Okay, thank you, and see you in the next video.